Hello friends, welcome to the Software World. I'm Can Dost. Here, I'm on a mission to make connections between the software industry and our individual and unique lives. We all have a common goal of solving problems with software. Whatever happens on our journeys will not stay mysterious anymore. Hello friends, welcome back to Software World with Can Dost. Today, my guest is Roberto Vitillo. Roberto is a principal software engineer at Microsoft. He has more than 10 years of experience in the tech industry in various roles, such as software engineer, tech lead, and manager. Prior to joining Microsoft, Roberto got his master's degree in Pisa and worked on scientific computing applications in Berkeley Lab. The software he developed are still in use in Atlas experiments and in the Large Hadron Collider. After that, Roberto joined Mozilla and worked in a variety of engineering roles. He worked on setting the direction of data platform from its early days and built the team and the platform. While in Mozilla, Roberto also graduated from Harvard Extension School with data science certificate. Roberto currently works in Microsoft and leads the ARIA pipeline, which is one of the largest data telemetry pipelines in the world, and it processes millions of events per second from billions of devices worldwide and supports many products such as Windows, Xbox, Office, Bing, and Skype. With this extensive experience, Roberto wrote a book called Understanding Distributed Systems, which is also the topic of today's episode. After I read the book, I approached Roberto to talk about distributed systems. In our talk during the episode, you will hear many things from distributed systems definition to CAP theorem, from memory leaks to writing a book and growing a career in software engineering. At the end of the episode, you will hear about how to get Roberto's book as a gift from me. So stay tuned until the end. Now, it's time to listen, learn, and enjoy. Welcome, Roberto. I'm really glad that you're here because after I read your book, I realized I learned a lot of things that I had no idea, which many details I still have no idea, but this is on me, not on you. This is the book that helped me to understand the picture of distributed systems, and now I can comfortably go on more details and read other books and getting to details of the things. But this was a perfect start for me as a beginner. This is the reason why I wanted to invite you to talk a little bit about the distributed systems. Most probably I will learn more about distributed systems and other things from you. Welcome.
Yeah, thanks for having me. And I'm very glad to hear that the book was actually useful to you. It sounds like it really hit the nail there in what I was trying to achieve, like giving someone that maybe doesn't have yet all the know-how, an overview of the whole field. Yeah, so I'm very happy to hear that you liked it.
Yeah, thanks a lot. It's a great book. We will talk about the details of the book later on, but I want to start with asking you my dumbest questions and start with these most looking simple, but I know it's difficult to define sometimes. What is a distributed system and what are the conditions of a system to be called as distributed?
Yeah, that's a good question. And to answer it, I'm actually not going to answer it directly straight away. I think we need to go a little bit back. Why do we even need such systems? Let me start with the why. So I think in the late 90s, probably only 2% of the worldwide population was online on the internet at some point. Then, of course, as you know, over time, more and more people joined the internet. And I think by now it's for sure over half the worldwide population. And what that means is if you have an online service, if you have an online business, then the total addressable market that you have keeps growing, right? And potentially you have more and more users. And this is where distributed system comes in. Eventually, you will hit a point where your little server, Apache server, won't anymore be enough to serve all your users, and you will need to somehow find a way around it. And for a long time, that answer has been, let's just buy a beefier machine, which makes sense. Like if you're a small company of one person, that's the first thing you will do, right? You're not going to go build some crazy distributed system just for the sake of it. But eventually, even there, eventually hardware, you won't find the hardware anymore. Things won't scale anymore. And this is where distributed systems comes in. So the idea there is to take off-the-shelf desktops or computers, put them together and build a computer which can serve more traffic than any single one ever could. So that's, I think, the initial need for distributed systems as I know them. And the thing that happens next is, if you have one box, say that machine fails once a year, has a probability of failing once a year. Now, if you have 100 machines, then any given day, you have the likelihood of any one of them failing is higher than when you had just a single box. And so the more stuff you start adding, the more components you start adding, the more total failures you will see. So the next thing that happens is, inevitably, you have to deal with failure. It will just be a constant in your life as an engineer working on such systems. And that's actually where my expertise lies, where I spend most of the time in, where probably most people in the field spend time in. It's like, how do we make systems resilient to failures? And kind of like the next challenge there, dealing with them. And then finally, the last one I will say is the operational side. Once you have all these components running, how do you release a new change comfortably? You won't break anything. How do you change configuration after the system is already running without redeploying everything? So all of these things become very important once the scale increases. So yeah, that's kind of like my answer to you. What is a distributed systems? There are many answers, of course. Like I guess if you work in a different field, you might have a different answer. I worked my career on like online applications, that sort of thing. So that's probably the answer.
I like the where you started, actually. When in 1999 or something, like in the beginnings of those things, it started from a really like, I don't know, as far as I remember, like it was started in the United States as a like maybe a bit military project, like whole internet thingy. And now when I think about it, like as web itself right now is a distributed system.
It is, yeah.
And now when I think, so doesn't it make every application using this system also a distributed system?
Yes, it does. It does. That's a very good point. Like, I think even as let's say you're a JavaScript developer, even as a JavaScript developer, you're actually dealing with the distributed systems. You're making remote calls to some remote servers, which might or might not be there. And what happens when it's not there? So yeah, we are all kind of distributed systems engineers at this time and age.
Yeah, so we have to learn the fundamentals. I think that's where I'm trying to go.
Yeah.
Like there is no other way, because I've been working with like software which uses web like for my whole life. And now I just blame myself from time to time. Like, why didn't I learn all the details until now? Like, because those are the things that helps to shape the mindset a little bit. And when you don't have the mindset, and when you don't know the really fundamentals, I'm not talking about maybe knowing every single detail, of course, but just knowing the fundamentals and being aware of them changes your mindset a lot.
It does, yeah. Like I feel like sometimes even if you're reading fundamental stuff, even without using that knowledge right away, I guess it sort of stays in your brain somewhere. And then eventually when you need to design or build something out, somehow you have these crazy intuitions. You don't really know where they come from, but I think your mind kind of like absorbs everything and then just puts everything together, and sometimes in the most unexpected ways. So yeah, fundamental knowledge is extremely important.
Yeah, these are usually helpful when we face with some challenges. And now I'm curious about what are those challenges in distributed systems. Like, for example, when I develop a mobile application, I know that network can be very slow and I need to react to it and etc. But I have the perspective from the outside, for example, developing a mobile application or developing a web application, but I don't have the intuition from the backside. So what are these big challenges of developing these distributed systems?
Yes, that's a good question. I would say the first one maybe is scaling an application, so scalability. And I want to start with this one because that's probably the most obvious one. That's what everyone thinks. Oh, I need to scale a distributed application. It's all about scale. Even the system design interviews that popularize the large scale system design, they always start with scale. So the thing is, scale is just the beginning of the journey. So, and as I was mentioning earlier, the more component you add, the more the number of failures will increase. And so that brings all its challenges, all new challenges with it. And so yeah, one of the biggest challenge is dealing with faults. So how do you stop a fault that happen on a single machine of propagating to other machines, to other services, and eventually bringing down the entire system with it? And there are many, many reasons why things fail. I will say the most common root causes of failures, I mean, there are many, but the one I will say top of mind is definitely networking or communication. So as you just said, like even when you build the mobile apps, you have to think about the network. And in the distributed systems, even more so, where your means of communications with other components is over the network. And the network is just unreliable. So the first thing you learn as you try to build a scalable application is that your remote call might never return. Your service you depend on might just not be there anymore. Your DNS might not resolve to anything. And so that's why in my book, I spent the first part of my book is all about the network. And initially I wasn't really sure, should I put it there? Should I even put this in a distributed systems book or not? It's kind of like an orthogonal knowledge, but I felt like sometimes engineers lack deep understanding of how the network works. And I wanted to, put kind of like a short summary to appreciate how this whole thing works. Also because the network itself is a distributed systems, and there is a lot to learn by understanding how TCP works and the core protocols of the internet.
When I read that chapter, like I said, wow, there are like many things. Every page, there are like 5 things I didn't know. And after I realized, now I understand. When I went back to second chapter, third chapter, and scaling and resilience and etc., I just realized, now I know what you're talking about. It's like this was the fundamentals. And one thing you mentioned there, like the resilience, and as we are recording this on October 9th in 2021, we just had a like really recent big outage from Facebook. I'm not sure if you know the details, but this is not an important right now. But there were also outages from Slack, Cloudflare, AWS all this year. And these are all distributed systems at scale. This is, I think, it's closely related to what you're saying, because from my perspective, I expect those services at scale to be more resilient. Like having this big outages, like full, like Facebook just disappear from the web, right? So it was not even reachable. That's the point you are telling. So why do we keep having these outages? Like what do these outages tell us?
So that's a good point. So I think in some ways, to answer your question, I feel like it's all about correlated failures. You will think that by adding more machines to your applications, you make it more resilient. So I have 10 machines. If one of them fails, I still have 9 left, right? That's what you will think in theory. But the problem is this argument applies only if the failure affects that single machine. If you have a faulty RAM module, then probably you will just lose that machine. Although in some cases, if you bought the RAM modules all at the same time from the same vendor, they might even fail around the same time, which is also kind of crazy. But the thing is, if you think about how the DNS works, like it doesn't matter how many machines you have in the back end, how resilient your whole infrastructure and your architecture is. If outside users can't resolve your DNS, you can resolve your DNS name to an IP address, they won't be able to connect to your system at all. So that's failure in the DNS brings down the entire systems with it. And the reason is because it has such a high blast radius. And I'm sure the people working on Facebook, they have thought about this, and those things do happen. It's like it's inevitable. Like we try our best to make them not happen, but sometimes there is some weird sequence of events that happen that somehow create this condition for a failure to have a crazy blast radius and bring down a large chunk of the system with it. So usually what happens is as the system grows, you have incidents like those. You have a postmortem. In the postmortem, there is a very long discussion in generally about learning how to avoid such mistakes in the future, but most of all, how to reduce the blast radius. So a very good question to ask is, okay, we had this failure now. How do we make sure that next time this happens, rather than bringing down 100% of the fleet, it only brings down half of the fleet, just to give an example. So how do we reduce the blast radius? So over time, you will see more and more failures. You will come up with better ways to be resilient against them, and the application becomes more and more robust. But the probability of failing never goes down to 0, and these things can happen.
So it's not a matter of if it's going to happen or not, but it's a matter of when it's going to happen.
Yes, There is always some weird side thing. The thing is, when you have a large system with so many components, it kind of has a life of its own. Like, it's very hard to think about all the possible states the entire system can get itself into. Humans try their best, but the reality is there are so many possible edge cases that when combined can trigger some weird outcome that you've never thought of.
Yeah, there are drills, right? When I read the Facebook's, for example, explanation, like why it happened, they also mentioned that they are doing a lot of drills, taking down systems to test if it is like really resilient and etc. These are a couple of strategies, but how, like for software engineers, let's say for me, for example, maybe a mobile engineer, web engineer, or like anyone who is not directly developing distributed systems, like on the backend side, how can we approach to be more resilient? What's the mindset here? Like, what are the strategies that should be built in this whole system design from this perspective and development process for these distributed systems?
So I guess the mindset there is in general thinking about what happens if this component fails. For a mobile app, you probably, I don't think you will think of what happens if the phone fails. Well, the phone fails, tough luck. But there you will think more, what happens if the server fails? What happens if the OAuth provider fails? Like, you start to think about things that can go wrong and how should your system react to it. So what I usually do during design time, I try to list all the failures I can think of, and I try to list them by risk. So the risk, one way to describe risk is the probability of the failure happening multiplied by the impact the failure will have if it happens. So that helps me understand where I should spend my time on architecting for resiliency. If, for example, if a failure has a very low probability of happening and the impact is minimal, I won't even care. On the other hand, if the impact is high, even if probability is low, then maybe it's a different thing. So typical, I'm trying to think of typical components that have high impact. I would say, single points of failures are top of mind. Any component where there's only one component, and if that component goes down, the whole application is no longer available. DNS is a single point of failure, because if DNS is down, of course, DNS by itself is also made resilient. Like, you have multiple DNS servers. There isn't just one server. You have the DNS services in multiple data centers, so that even if a data center is down, the other ones can take over, and so on and so forth. But yeah, that's kind of like the mindset I have.
That's a good mindset. And now I want to pull a little bit back and come into the part that is more related to coordinating systems, because we are talking about multiple machines and etc. But all the time, whenever I took a look at distributed systems, I see one theorem, CAP theorem, which always there. Everyone talks about it whenever we mention, and everyone says it's not solvable. Like, the CAP theorem, from what I read, is it's the picking two things out of three, which are consistency, availability, and partition tolerance, and you sacrifice the other one, the third one. But in your book, that one title, like, when I was just taking a look at the table of contents before reading, and I saw solving the CAP theorem. It's like, everyone told me, like, this is not solvable. And this is the first thing I read, by the way. And I'm curious, like, from my beginner's perspective again on distributed systems, can you explain how we approach to solve this to the people who are listening us?
Yeah, so the reason why I put the catch title on purpose. So the CAP theorem applies for a specific type of consistency, which is strong consistency. So, but it doesn't say anything about other types of consistency. So strong consistency means if you perform an operation, and let's say you're making a request to your service to do something, when you get back a response from the request, you can assume that everyone else will see the side effects of that request. So that's one way to describe strong consistency. But there are other types of consistency, like, for sure you're aware of, like eventual consistency. So in that case, the CAP theorem doesn't really apply as it's stated. And so when I used the title solving the CAP theorem, I really meant working around it. That was it. So, and in fact, the whole section talks about how to leverage other types of consistencies to build systems that are available, consistent not strongly though, and partition tolerant.
Yeah, that was the part because like I remember still, I think I have a lot of notes around it as well. One thing that I realized there also is, as we talked in a moment, network will fail. So we cannot avoid this one. It's usually about choosing what's like is consistency and partition tolerance. But anyway, this is one thing that kind of surprised me when I was reading the book. But now the one other thing that you said in the beginning, and distributed systems require big operations and operation management behind it. Once we have these multiple nodes around the world, we need new ways to manage and operate those systems. So what are the best practices and what are the must-haves in those best practices to manage this everything?
I will say that the first thing that comes to mind is strong observability or monitoring, if you prefer that word. The first thing is you need to know what's going on. You need to monitor your system. How many failures are users seeing? How many machines are down? How many requests you're processing? How many exceptions a specific service has encountered? So you pretty much want to know everything there is, even if you think it might not be useful. Maybe during an incident, that information will be useful. So logs and metrics are very fundamental techniques that help understanding the system when it's running. And what you can do with metrics is then use alerts, build alerts on top of it so that you can be paged when something that shouldn't happen is happening. So alerts those are very simple techniques, but I've seen or talked to many people that worked in places where even the most basic metrics weren't there, or where no alerts were there. And so what happens is like the entire system fails and they find out that their service is down because a customer emailed them. So that's definitely not something you want to happen. So yeah, those are the bare minimum that you should have. Very simple. There are many tools these days to get metrics and logs out of the box, and you can instrument your own application. Yeah, so once you have those, the bare minimum, you also need to think about how you release changes. Because once you have a large application production, any change, releasing change is very scary, right? You can bring down everything with it. So how do you release a change in a safe way? So then deployment pipelines come in, that you staged deployments where you deploy first to a very small fraction of your fleet. You let it bake in there for a long time. You use metrics and logs and alerts to make sure that nothing is going on, and then you continue slowly your deployment. Thing you need to be aware of when operationalizing a big distributed system. And the other one is, I will maybe call it manageability, is how easy is it to change the system without any code changes when it's running? So you might have to make some changes at runtime because there is some kind of failure going on. So you have to reconfigure your system. Is it possible to do it without waiting a day for a deployment? So yeah, that's the thing. Like, so you need to have some system in place where you can make configuration changes in a safe way. So they also need to be rolled out slowly, but you can do those changes without redeploying the entire application. So that's another concern as well.
I always saw that it's a restart. I think I never seen, or maybe we have it, but I have no idea about those systems. But whenever there was like, okay, this is not working. Okay, let's redeploy. And it takes 30 minutes.
You're saying something. The restart is an interesting thing, right? Like many times it works. And we actually, some of our services have what we call the defibrillator, which is like a watchdog process that looks whether the process actually handling request is doing something. And if it's stuck for whatever reason, because I don't know, maybe there was a memory leak and the process slowed down so much that it barely processes anything anymore, or maybe there's a socket leak and it can't open connections anymore and basically the process stops. So this defibrillator basically is very stupid. It just sees whether the process is doing anything, and if it feels like something is off, it just restarts it. Very dumb, very helpful. Because the thing is, even with C#, we use C# at work, we used Java before, Scala, whatever. Even with managed languages that have garbage collection, you can introduce memory leaks. So these things will happen. Like I cannot predict all possible memory leaks that will happen. I'm sure somehow they will get in the future. So this dump restart mechanism helps you buy some time to actually go and fix the root cause, rather than having the entire service at some point just stop working because they all ended up without memory. So these things, they're silly, but they work sometimes quite well.
Yeah, it's like that's what I use like mostly. I either restart the service. I think there's like some automated restarts directly watching as you said, but sometimes that doesn't work, and I don't know, instantly without thinking about it, I just think, okay, let's restart. I remember this one from more like a IT crowd TV series. Like there was an episode
Yeah,
they they were calling the IT and it's like, did you restart your computer? Ah, no, that's a good idea and it works. Yeah, like
yeah. That's so. The thing is about the restart is your application has a steady state. So, or let's say an HTTP service has a steady state. So this is state. It's the most common state. It's the one where everything is working fine, and the application spends most of its lifetime in this steady state. Your human brain also kind of the mental model you have about your system is the steady state. When this weird thing happens, your application starts behaving in a different way. So we call it a modality change. So these modality changes are very dangerous because your entire design, you architected your application with this steady state in mind. And so whenever you enter in a new mode of operation, it's very dangerous. So the restart actually kind of resets and brings you back to the steady state many times, but not always, and that helps. But an example where this won't help is, for example, let's say you have a large scale front end that is processing many requests from around the globe, and you have an entire region going dark. Maybe there was a electrical storm or something and brought the region down. For whatever reason, the region is down. So now the other machines in all the other regions are taking over the traffic of the region that went down, and they are processing way more than they used to before. Now they will, depending on how it's architected, they can degrade because they're just running at maximum CPU, they barely can handle the traffic. They will degrade. In that case, if you were to restart, restart won't help. It will probably make it worse because during the restart, you actually even lose machines. And so, the restart is sometimes works, sometimes not. But depends on the situation. But it's uncanny how powerful this very simple mechanism is.
at the end we have to have monitoring to be able to understand what's going on. And I think
Exactly.
the most companies or most projects I have seen that they lack monitoring a lot, because those are the systems that you usually don't go and monitor things when everything goes fine. But whenever something goes wrong, that's the part that is going to help you once you can identify. And there are so many other things, of course, we just didn't talk about. It's in your book. You put all that information and way more things into the book. And the book name is Understanding Distributed Systems, which I have understood a little bit more than I knew before. I was totally ignorant to distributed systems. Now I know a little bit. But why did you write this book? Like, what was the motivation to tackle this writing challenge? Because I know it's a big challenge. I know from my writings, because I write articles on my blog. And that is a challenge, like writing articles is a challenge for me. And writing a book, I even can't imagine. Like, what was the motivation to tackle this big challenge?
Yeah, that's a good question. So it actually started, I didn't want to write a book initially. So what I wanted to do was to do a little product in my free time. I just wanted to have a product where I could learn a bit more about marketing, sales, and actually very little. I didn't want to do any coding at all. It was very deliberate. And I was thinking, okay, what is the best thing to learn all those other skills that I don't have without spending too much time on the engineering side? So I thought, okay, I already have some knowledge. I get paid for that knowledge. Maybe other people will find it useful. So then I said, okay, writing a book about something I know well will help me spend more time on these other things that I don't know how to do well. So that was the initial thinking. And initially, to be honest, it was supposed to be a system design interview class. That's how it started. And I did all the things you should not do if you just want to make a product. So the market for system design interviews is huge. There's a lot of demand. People are willing to pay for it. And when I started, it seemed like a good idea. But then I realized that in order to pass a system design interview, in many cases, you actually don't need to be an expert building such systems. Because often what happens is companies will ask you this question just because Google, Facebook, Microsoft ask these questions, but they themselves don't have the expertise to evaluate you on those problems. And so I realized I was doing a disservice there. Like I was going to teach people how to pass interviews, but I wasn't really going to teach them how to build the systems, really build the systems. So I felt like, okay, I want to go more on the actual, here's what the job entails. And maybe you don't need all the stuff for an interview, but if you're actually gonna ever build such a system, then my book will be useful to you. And so, of course, the crowd of people that are interested in learning the fundamentals is very different than the crowd that just wants to pass interviews. It's much smaller, and that's fine. Like I didn't do it for the money. It was just like I wanted to have an experience building a product that people will like. And so that's why I kind of pivoted to this book and slowly became a monster of its own. And it still is, because I keep updating it, and it's just time drain. But hearing from people like you that they found one thing, they somehow learned one thing they didn't know before, that makes me really happy. It means it's useful to someone.
Yeah. When I got this book, I must be honest, like I was saying, okay, let's see this system design interviews. Let's tackle this. And I just said, okay, to be able to pass this interview or maybe hold by myself to test others in the interview, I need to learn. And this was my starting point. And I just saw this book. I don't know where, maybe on Gergely's website. I'm not sure. And I said, okay, this looks good. It's short enough, because other books, like, I don't know, some books I saw 500 pages. It's just frightening, it's like 500 pages to just pass the interview. I won't read it. Like, I need the information, like the simple one, because I already have some knowledge about developing software systems and etc. I just need to be able to think in that way. That's why I bought this book. I must be honest, I passed 2 interviews thanks to this book. So I did not change my job, but that was the challenge I put myself. I was like, okay, I'm going to try. And I just read this book, and I just watched some other videos on YouTube. That was all. That's all I did. And it helped. That's what I'm trying to say. And also, one thing is the language of the book is so fluent and smooth. And even though there are many technical terms that I didn't know, I understand them easily. How did you translate this technical language to a language which almost all software engineers can understand?
I guess when you write a book, there are many reasons sometimes to write a book. Sometimes you just want to say, hey, look how awesome I am. I know all this stuff. And you write these super technical things that very few people can understand. And that's more in, I guess, in academia. It's more, maybe it happens more often there. In my case, I try to put myself in the shoes of a beginner or someone that is a very strong technical person, but maybe doesn't not had yet the chance to work on such systems. Every time I write, I reread it 100 times. I think, okay, if I had to explain this to a new coworker that we just hired without previous experience, will that make sense to him? So I really strive to do that. It's not perfect, far from it. Every time I reread the thing, I realize something is not right and keep changing and fiddling. So that's why it's also a very time-consuming process. The thing I dislike about writing is that when you write code, you have unit tests and you can refactor things easily. In a book, instead, if you change your mind about the term, man, you have to go back, change everything by hand. It's so time consuming. It's just crazy how much time it goes into this sort of simple things.
This is why I like writing, to be honest. Like, yes, in software, we get used to so many like these automations and unit tests around it. Okay, I mean, if I make mistake, they will catch it. It's like, if I change this and I break things, they will catch it. But in writing, there's no such things. If someone comes to you and says, then like there is no monitoring as well. Like if you think about distributed systems, it's so out of the things that we got used to it. But one thing I realize is that once you want to grow in your career, you have to learn how to explain those technical things to non-technical people, to beginners. That's must have. Otherwise, you really cannot learn and grow in your career.
Yes, as an engineer, at some point, it doesn't matter if you want to go into management or you want to stay an individual contributor. You need to be able to communicate really well and get buy-in from your peers, from coworkers, from people above you. And writing is incredible useful skill there. And I'm not just mean being verbose. No, it's just being very clear and very direct, getting to the point, trying to make good arguments. So eventually, I think to grow as an IC, that becomes a very, very important skill to have. I will say definitely much more than coding. I think there's some point where most people just plateau on the programming skills, because you are a good enough coder, I will say, that you can solve most problems and there's not much you can improve there. But it doesn't matter how good at coding you are if you cannot convince other people or of something or make good arguments for it or even change your own mind with other ideas. So yeah, writing is very important. The other thing about writing is it helps you put your thoughts together. Like I feel like when you have to write something down, that's where you have to truly understand what you want to do or you're trying to say. So it's a thinking tool as well.
Yeah, I like to call writing shapes your thoughts. And yeah, to be able to understand what you're thinking, you need to write it down. Otherwise, they're just something in your head. You have no idea what thought is connected to other one. It's just a cloud. When you write it down, it gets a bit more clear, everything.
So sometimes you write something down and you realize you actually don't understand it.
Yeah, thanks a lot. I really enjoyed our conversation. It was so pleasure to have you here. And for the people who are listening us, that's a gift from me. If you send a tweet to Twitter mentioning me and Roberto, then you will get into a lottery, let's call it this way. And I will gift one ebook of Roberto to our listeners. And thanks out, Roberto, for writing this book. I'm just holding the book in the printed version in my hand. I'm kind of regretting that I didn't get the ebook version because it has the updates. But this one, I just have this. But most probably, I will buy the new versions as an ebook. But thanks a lot for writing this book. It helped me a lot to understand many things around distributed systems. And thanks a lot for joining and for taking one more step, teaching me more about distributed systems and writing in this podcast. Thanks a lot.
Yeah, thanks a lot for having me. You're a great host. It was a pleasure being here.
Before you go, it's just a 1 second. As I said a minute before, I'm giving Roberto's book as a gift to one of the followers of the show. If you share the show on Twitter with mentioning me and Roberto, you will have a chance to win the ebook version of Roberto's book. But if you don't have a Twitter, don't worry. Just send me an email and write about what did you like the most in the show, and you will also get a chance. You can find my Twitter and Roberto's Twitter handles on the description or on jandos.blog/podcast, or you can send me an email at podcast@jandosdagdevrem.com, which you can also find in the description. Additionally, don't forget to share the episode with one of your friends, colleagues, or work friends. Until next time, take care.